Kind of sounds like antimatter, doesn't it? Or anti-whatever. Anyone want to guess what an antiderivative is?
Is it like antimatter?
No, it's not like antimatter. Sorry.
Does it make things flow?
What'd you say, Tilly? It's the inverse of a derivative. It's the opposite of a derivative. So an antiderivative undoes a derivative. So the idea of an antiderivative is if we take a function and we take the derivative of it, and then we do the antiderivative, we get back to where we started. Yes? It is. Yes, kind of, sort of, but not quite. So let me give you an example here. Let's say that I give you the function f of x equals x squared. Then the derivative of that function is f prime of x equals 2x. Now, had I not given you this function to begin with, let's get rid of it. Could you have told me what the function was to begin with if I told you that the derivative of the function was going to be 2x?
Yes.
Okay, and how would we do that? Do the opposite of what we did to get the derivative, right? So to do the antiderivative, we would say, well, okay, instead of decreasing the exponent by 1, we would increase the exponent by 1, right? So instead of a linear function, we would have a squared function. And then instead of multiplying by that exponent, we would divide by that exponent. And so we would end up with just x squared. Do you agree with that? Okay, well, here's where we run into trouble with antiderivatives. What if the function was this? Is there any way, first of all, let me ask this. Is this derivative correct for this function? It is, right? Is there any way for us to look at this derivative and know that we should have had a plus 1 there? No. What other types of things could I put on here instead of a plus 1? I could put really any constant there, right? So the antiderivative of 2x is not just x squared, but it's going to be x squared plus a constant. So it's going to be x squared plus c. All right, so what that does, that plus c takes into account the fact that if we were to take the derivative of this, that c is just going to go away. And there's no way to know what that constant is just given the function. And we'll talk about how we account for that later on. All right, so here's something that we're going to have going on. This is the same function I showed you earlier. There's two functions here. And these two functions have the same slope at any x value. What's the difference between these two functions?
One's been shifted.
Yeah, one of them's just been shifted up from the other, right? G of x is f of x plus something. Well, what are the derivatives of g of x and f of x going to look like? They're going to be exactly the same. So the idea here is when we take the derivative of two different functions that differ just by a constant, their derivatives are going to be the same. All right, so when we do antiderivatives, we are going to have to take that into account. We're going to use a variable, a c, to represent that. So we want to find the function whose derivative is sine of x and whose graph passes through 0, 2. Let's ignore this second part here. Let's ignore this whose graph passes through 0, 2. Let's just find some function, any function, whose derivative is sine of x. Any ideas how we could do that? Negative cosine? Why negative cosine? Okay, so we know that f prime of x is equal to sine of x. So that means that f of x, let's say I didn't know it was negative cosine. First of all, we know that the derivative of sine is cosine. We know the derivative of cosine is negative sine. So I know that the derivatives are very closely related. I know it's going to have something to do with cosine of x. Well, I tried cosine of x, and is cosine of x going to work? No, because the derivative of cosine of x is negative sine of x. So to account for that, that's where we get the negative there. So we know f of x is going to be negative cosine of x, but does it have to be negative cosine of x? No, what could be different about it? Yeah, it could differ by any constant, right? So it could be shifted up or down in the coordinate plane however much we want. So we're going to add some constant on here. So we know that the function is going to be negative cosine of x plus some constant. And if I were to take the derivative of this just to check my answer here, the derivative of cosine would be negative sine, so the derivative of negative cosine would be positive sine. The derivative of our constant would be 0, so that would drop out. So this equation right here satisfies what we need for our function. So let's go back here then and use what we're going to call initial conditions. So we're going to use initial conditions here to determine what that c is. So I know that the graph of this is going to go through 0, 2. How can I figure out what c is using that 0, 2?
Plug in 2 is like x and plug 0 in cosine.
Yeah, exactly. So we're gonna put 0 in for x, and we're going to put 2 in for y, or for the function. So to figure out what c is, we're going to do this. 2 equals negative cosine of 0 plus c. So what we're doing is we're using these initial conditions to figure out what c is going to be. You guys know what cosine of 0 is? 1. So negative cosine of 0 would be, and so c is going to equal 3. So then what is f of x going to look like? Since c equals 3, what is f of x? Negative cosine x plus 3, or you could write it as 3 minus cosine of x. That would be a little bit cleaner probably, but either way works. Does that make sense? Okay. So just formalizing some stuff here. The process of finding the original function from the derivative is called the antiderivative. A lot of times we use a capital F to represent the antiderivative. Oops. We use the capital F to represent the antiderivative of a function f of x, so that the derivative of that capital of f of x is equal to the lowercase f of x. And what we need to do is we need to account for losing constants when we take the derivative by adding an arbitrary constant in there. That's where the plus c comes from. Okay, we're going to do a lot more with antidifferentiation. As Lewis said, that's actually called integration in some uses. And integration and differentiation are inverses of each other. And so we're going to spend a large, significant amount of time talking about antiderivatives and integrals later on. This is just kind of an introduction to it. All right, so let's do one more example here. This is a physics example. In fact, those of you that are taking physics, I'm guessing you've probably done some examples like this. And what we want to do is we want to find the velocity and the position functions with these conditions. We know that the acceleration due to gravity is 9.8 meters per second squared. And so for this particular object, we know that it's going to start with an initial velocity of 1 meter per second downward. The first thing we want to do with a problem like this is we want to set up some parameters here. We want to decide which way is going to be positive, which way is going to be negative. It really doesn't matter which way we do it. We can say that up is positive, and we just have to make sure that we're consistent with it, or we can say down is positive, and we just have to make sure we're consistent with it. Both have advantages. Up is kind of the natural positive because up is usually positive, right? Why might downward being positive be advantageous in this problem? Vimmel?
Get rid of the negative signs?
Yeah, we get rid of the negative signs, exactly. So we have a downward acceleration, and we have an initial velocity that's downward, so everything's going down. So if we make downward positive, everything's going to be positive. If we make upward positive, then we're going to have a negative acceleration, we're going to have a negative velocity to start with, and there's nothing wrong with that. We're just going to end up with some negatives. So which way do you guys want to go? We'll do this by vote here, or by, what's that? Down is positive? All right, Tyler says down's positive. All right, so I'm going to indicate that here, just make sure that we keep that straight. So downward's going to be positive. So we know what the acceleration function is. The acceleration, and I'm going to put it with respect to time, the acceleration with respect to time is what? 9.8. Now the units on there are meters per second. Meters per second squared. We'll as we go along here, we'll look at the units, but we'll talk more about how units are affected by differentiation and anti-differentiation later. All right, so the acceleration is going to be 9.8 meters per second squared. So how do we figure out what the velocity is? How are acceleration and velocity related? Acceleration is the derivative of velocity, right? So then velocity is going to be the antiderivative of the acceleration. So if we have an acceleration function of 9.8 meters per second squared, then the velocity is going to be the antiderivative of that. So what would I take the derivative of to get 9.8 meters per second squared? 9.8t plus some constant. And what are we going to do to figure out what that constant is? We're going to use the given information that the initial conditions here. In this case, the initial velocity is 1 meter per second downward. What are our units on velocity going to be? It's going to be meters per second. So that's consistent with the initial velocity here. So if the initial velocity, what does it mean when initial velocity is 1 meter per second? What's the time going to be for the initial velocity? 0, right? So we know that v of 0 is equal to 1. Why not negative 1?
Because we said the acceleration is positive.
We said downward is positive, exactly. So how can I use this with this to figure out what c is? Plug it in. So we're going to say v of 0, which is equal to 9.8 times 0 plus c, is going to be equal to 1. And so that means that c is going to equal 1. So we got c equals 1 there, which means that our velocity function now is 9.8t plus 1. Does that make sense?
Yes.
Okay, Vimmel says yes. Does everybody else agree?
Yes.
All right. So now we have the velocity function. Now we want the position equation. Position, I'll go ahead and use x. You guys like x for that, right? Okay, I'll use x for position then. Velocity is the what of position? Derivative. So then that means that the position is the antiderivative of velocity. So what would I take the derivative of to get 9.8t plus 1? Let's just do it one part at a time. When I take the derivative, the exponent decreases by 1. So when I take the antiderivative, the exponent is going to increase by 1. So I'm going to have something times t squared. Now, when I take the derivative of this function, I'm going to take 2 times whatever's out front to get 9.8. So instead of multiplying by 2, I'm going to take the 9.8 and divide by 2. So we get 4.9. You guys agree with that? All right, then looking at this term here, what would I take the derivative of to get 1? T. And plus some constant. Now, is there anything in this problem that can tell us what that constant is going to be? Okay. I made probably a mistake here. I used C here where using C is probably not a good idea. Why would C not be a good idea here?
Because you stated what C was earlier.
Yeah, we already found a value for C. So here I might want to use a different variable. I might use K, or I might just use a subscript here and say C1. Or I could use C1 here and C2 here. But be sure that you're not using the same variable to represent different things. It actually turns out that this constant right here is going to be the same as your initial velocity. So a lot of times, you guys probably, I'm guessing, do this in your physics class, use V naught there, right? V naught, naught is N-O-U-G-H-T, like V0. So V naught, and then this right here, this constant C1 is the same thing as the initial position, so that would be X naught. So this V sub 0 just means the initial velocity, this X sub 0 just means the initial position. We don't know what the initial position was here in this problem, so we'll just leave that in there. Anything else we have to do for this one? Does this make sense?